Okay, so we move on to the next session. This is by Sini Balakrishnan from Intel. So let me introduce Sini while she is climbing up. So Sini is working as a formal verification team. She is leading working there as a lead architect in Central Tech Office, FVCTO, which is a prestigious organization within the Intel. And she has tons of experience in using formal. She has worked in different domains of formal, applying that in wireless, wireline, in automotive and memory domains during her career. She has lots of trade secrets and patents. I think one of that she is going to unearth, that is applying hashing algorithms in verification. So thanks, Sini. Please go ahead.
Hi all. Hope all enjoyed today's swim in the morning. This is, so we all use social media a lot, right? Some of us. And some of us are even addicted to that. And the term hash is very common to us in the name of hashtags. And that is mainly to tag some information and or some articles and retrieve based on that hashtags. But the hashing which we are discussing or which I'm going to present here is something related to the multiple processors and the cache nodes in communicating with the memories using hashing. So this is mainly on the hashing, address hashing algorithms and challenges involved in that, and how our end-to-end solution resolve those challenges. So here, as I mentioned, we will be discussing about the address hashing and the design where we have used these address hashing techniques, and because it's used in like SKUs, stop keeping units in Intel, where any associate should be able to use this hashing algorithms. And there are lots of verification challenges involved, and that also will be discussed, and our A to E verification methodology to verify from architecture to the implementation. So here it is like an input address will be like coming from the multiple processors or the cache nodes, and that will be converted using some mathematical algorithm. It will be converted to a hashed address where actually that will be the memory address where the data has to be stored or retrieved. And why we use hashing? Mainly one is the address mapping, and this is actually helps to avoid the collision. So if two input addresses map to the same address, or two different input addresses should not map to the same address. So if that is called address aliasing, so hashing will help to avoid the memory collision. And it actually supports different modes, multiple modes. And another important part is the memory load distribution. So we are using multiple memories, and from the multiple processors or cache nodes, whatever the request comes, it has to be distributed among all memories available. So that is the load balancing check. So that has to be taken care in the architecture itself. So here the design which we have used is where the hashing algorithm is used in the cache controller IP. So this is a high performance graphics SoC. This is from the L3 nodes to the GDDR. GDDR is graphics double data rate memory. And to familiarize with the term, the flow manager is AFM, which is part of that our cache controller IP. But this request is coming from the L3 nodes because our cache controller is L4. And here we have that AFM or L3 nodes requesting, and the AFM will classify the transaction and decides whether it has to go to the cache or to the memory or to the GDDR. So here, based on, now we are not talking about anything which is going into the cache, but it's to the GDDR. So here we have an hashing algorithm sitting inside the crossbar, and that will be mapping the address from the AFM to the GDDR. the corresponding GDDR, because we will have the multiple L3 nodes and communicating with the multiple GDDR. That configuration settings will be coming in the next. So this is for the X3 subnet. This is one single subnet which we are talking about. Here you can see that 4 AFMs and communicating with 3 GDDR. This is called the 4:3 configuration. And if 4 AFM communicating with the 2 GDDR or 4 communicating with the 4 GDDR. So this is based on the X3 subnet configuration. So you can see that there are lots of combination possible. So, and a different configuration will lead to a different algorithms, hashing algorithm. So here you can see that we support X2, X3 and X4 configurations, and even X2 configuration we will have the 3:1, 3:2 and 3:3, which is we call as 1:1. Same for the X3, 4:3, 4:2 and 4:4, and for X4, 5:4, 5:3 and 5:5. But each of these configuration, different address ranges would be supported, and different hash modes will be supported. That means hash modes in the sense whether the page is 256 byte or 512 or 1 KB or 2 KB, all 4. So coming into the complete configuration which we have to support is huge. So this is one challenge which we have because validating all configuration is vital to avoid the respins. So I already mentioned we have to, the second point is the multiple operating modes, not to GDDR ratio. No to GDDR ratio is that AFM to GDDR that I have mentioned, and it supports some multiple subnet, multiple hash modes, and multiple node to GDDR ratios. And other challenge is it is algorithmic complexity, because it uses mathematical algorithms to convert your input address to the output address. So that mathematical algorithm involves some of the division operator, mode 9 operator, etc. So that is algorithmic complexity is another verification challenge. We all know that formal property verification is not able to handle that. So we have to come up with a different approach on that as well. And the another point is on the vast address space. So you have a huge address space to be covered for example, the AFM and the GDDR side. So this is another thing which we all know cannot be verified using the traditional approach. Now coming into our E2E hashing verification methodology, which covers the architecture till design implementation. So architecture means you start with the specification till the implementation. So this ensuring the correctness of architecture or specification, and then we have to cover the algorithmic block implementation, and then finally we have to ensuring the implementation correctness, that is the RTL correctness. So all three will be covered in this. So here this is a pictorial representation where we are covering the architectural specification and the hashing algorithm implementation. And there are 3 different formal technologies used in validating the complete hashing algorithm from architecture till implementation. That is, one is formal property verification, that is for the mainly for the hash algorithm implementation verification, and the ArchFE or architectural FE we have used for the specification or the architecture. And the data path is specifically for the data path specific like a mode and div algorithmic complex block. So now let's go through the architectural verification validation. So architecture validation, we do modeling, and the modeling will be formally verified. So this is the 2 stages. So the modeling means what we do. We do it in Python. Python modeling, whatever the specification says, that will be that is done in Python. And you can actually use the Rainbow framework as well. So it's like a modeling will be done on the higher level of abstraction, and Z3 SMT solver is used to satisfiability modulo theories used to validate this. Okay, say it's satisfiable or not. So we have this, means there is a Z3 Python wrapper is used to integrate this our ArchFE model with the Z3's SMT solver. So this is the way it has been done. Architecture validation has been done using this, using the Z3's SMT solver. And there are some of the checks, important checks, which we have covered in ArchFE. So one is actually the address aliasing checks. So no two address should not generate the same output address. So this is a kind of, we have that multiple AFMs and multiple GDDR involved. So our AFM ID and the input address must result in the unique GDDR ID and the address. And output validity check means the entire AFM should fit into the GDDR address space. So all valid address, AFM ID address combination should have a valid GDDR ID address combination. And other one is spurious check, as it is like it's a negative, that is output address. There is a valid input address. That means that there should be a valid input address in the sense AFM ID address combination. So another important one is on the load balancing. Load balancing means for example, we have X3 configuration. If you take X3 configuration, we have 4 subnets, and each subnet have 4 AFMs. So we have total 16 AFMs. And when you take a 64 KB page, and it is 4 KB aligned, so we have 64 by 16. That is why it is called like 4 KB aligned. And there we have a 4:3 configuration. We have GDDR 0, 1, and 2. So this can be, the distribution pattern can be 556, 565, or 655. So the address distribution for GDDR 0, 1, 2 will be 556, 565, or 655. And another criteria which you have to follow is 264 KB page. If you take it, must not repeat the same pattern. And when you take up the 364 KB page, it has to be cover all 3 distribution. Then only each GDDR will have all GDDR will get the 16. So it will be fully distributed, and the load balancing is happening with that. So this is an important architectural verification, validation checks. Next is about the implementation. So architecture specification we have validated, and we got a clean specification. So, and the implement designer has implemented based on that. The implementation validation is using FPV, formal property verification. I think it's kind of very familiar now, and it doesn't need any stimuli, and no complex formal verification environment like UVM and all. It's very simple, and you just have to model and some of the assertions, and you are able to validate the algorithm. So it is actually able to cover the entire space except the algorithmic blocks. So entire hashing algorithm except the algorithm blocks was able to cover using FPV. So on the algorithmic block side, we have used the DPV, data path verification. So this is mainly for the mode Div3 and mode 9 block. And this is, we have used RTL to RTL data path validation. And this is mainly for example, if you take Div3 and you have a booth, it's a golden is simple math division operator divided by 3. But your implementation would be like a case switches with both multi algorithm. So it's like you compare this RTL to RTL. So RTL to RTL data path validation tool is able to solve this Div3 and mode 9 validation. It is like a simple mode operator and on the mode 9. But it is implementation was using the bitwise manipulation. This is mainly for the effective implementation. So this is actually data path validation on the algorithmic blocks. So now we have covered all 3, like your specification is covered using architectural FE, and your implementation on the FPV and data path together, the implementation validation is done. And some of the checks, important checks which we have used in the implementation validation, one is on the address aliasing checks. So how we are able to cover the entire address space? We have a symbolic modeling. So we have the symbolic input address, input 1 and input address 1 and input address 2. So you are making sure that your 2 input addresses are different. So symbolic addresses, you are not constraining anything, so you can have the entire address space of AFM. So this is, and there are 3 so the latency is 3, so we are waiting for the 3, we have a counter to make sure that the output is, output availability, to track the output availability, the counter has been used. And we are validating that the GDDR address, that output address, hashed address is different. If it is same, it is port selection will be different. So this is an important check, and as it is actually able to, as I mentioned, it's actually the symbolic modeling is used, so it is able to cover the entire address space. So other checks are like port selection logic. Port selection logic, we have actually our own model. FE modeling we did, reference model we have done, and we are our checker will be comparing this FPV output from FPV with the design FPV, design output. So next is about the spurious output check. This is kind of making sure that there is no wrong logic to generate the particular address on the GDDR. So this is making sure that there should be a valid address for every output address. Next is the hash value. Hash value is the actual hash generation logic. That is, we have our own reference model to implement it, and that checker is validating that or the hashed address and the design hashed address, FPV hashed address and the design hashed address are matching or it's equivalent. So this is the overall implementation, overall flow. So there are, I already talked about RHFE, DPV, and the FPV. So we have the hashing algorithm, a high-level architectural specification, and that will be going through the architectural FE. As I mentioned, it's a huge set of configurations. Also all X2, X3, X4 subnet for the entire address space we're able to cover because it's formal. And architecture, so that way architectural hashing algorithm has been verified. And the data path covered our mode and div, which was kind of tough to cover in the other FPV run. So data path validation done for the mode and div, and the formal property verification was able to cover the entire X2, X3, X4 with all the configurations which we have mentioned. So I mentioned about the multiple configurations supported, and that configuration was able to cover using some of the task-based approach, where we have the set of checkers would be same, but kind of same, only few constraints will be different, and using from assume minus from assume minus means hyphen from assert will convert the assertion to the assumptions, and then we are able to use the those assertions as an assumption for the respective task, or the just mentioned here like different modes will be based on the task. So about the results, we were able to cover the entire hashing algorithm verification in like 3 to 4 weeks, because RHFE, parallelly RHFE and FPV were going on. And this is actually uncovered 3 architectural issues and 1 implementation issue. And architectural issue was, one was related to the load distribution, and that was actually helped to improve the performance. And other one is on the wrong address generation in the architecture FE. So the architect were able to clean up the specification and based on the architectural FE feedback. And some of one 5:2 configuration, we were able to detect the wrong port selection, that is on the implementation side. So another important point which I actually want to take out again is the sweep through the entire address space on the address aliasing checks, which we would have not have been covered in the normal traditional verification. And about the overall thing, I would say that it's an end-to-end solution for covering the architecture till implementation, and kind of checks like load balancing, load distribution have improved, helped us to improve the performance of the architecture, and complete address aliasing checks to cover to the entire address space help us to get the good confidence on the quality. And so we can say that we were able to cover the entire caching algorithm till implementation using this formal technique. Thank you. Any other?
Thanks, Siri. Thanks, Sini. Questions?
This seems
We
like,
have questions from here and here. Yeah, go ahead, Rajesh.
yeah, this seems like a good candidate for C to RTL verification. Was the feasibility explored? Hello. This seems like a good.
Sorry?
This seems like a good candidate for C to RTL verification, having your hashing algorithm written in C and then verify against the implementation. Was it explored? Was the feasibility explored? Was the model available?
Yeah, we have actually done that as well, the C2RTL. Yeah, because we have a good team on working on that as well.
Yeah, we have one more.
So for architectural FP, any reason for using Python and not SV?
SMT solver is supported, means Python is supported in Z3 SMT solver.
Okay.
So Python or Rainbow framework, these two are supported. So the C3 is actually from Microsoft open source.
Okay.
Yeah, it's a constraint solver which is used.
So can we use these kind of solvers for verifying architectural level issues in, let's say, CXL or some other protocol?
Yeah.
So was your question on can we use Z3 for various architectures? See,
Like how to differentiate when to use these
Excellent.
EDA tools and open source?
good, good. So see, we have a specific team on the architectural formula. We have a team of almost 10 PhDs working on the architectural formula, right? So there are multiple architectural tools. I mean, when we start with the new SMV, Z3, Coq, even the Promela spin or Murphy, right? So each one of those could be used for different architectures. For distributed architectures, there is a different tool. For the concurrent architectures, it's a different tool. And for the data path, it's a different tool. The SMT solvers are different for different problems. So this particular problem, hashing problem, is more data oriented, where the Coq or the ACL2 or Z3 are the right tools to be used. So we have a specific methodology where to use what.
Okay.
Yeah.
Thanks. Thanks, Kiran.
Thank you.
Hi. So since there are multiple configurations in this algorithm, right? So did you run formal separately for each of these configuration, or did you take care using some checkers?
The question, can you please repeat? You
Yeah.
were
So since there are multiple configurations, right,
Okay.
in this algorithm, so did you run formal separately for each of the configuration, or
we don't need to run, means we have to run, but you don't need to, you can actually use the task-based approach. So this is simply vertical script. You can just modify your assumption to assertion, because some of the cases it is an assertion or assumption. Depending on that, you vary that and just run it. The entire task can be run in one regression itself.
Okay.
So you don't need to validate it separately. You can actually have an entire task in one tickle, and you just have to run it, the complete list.
Okay.
So yeah, that will help to resolve all the configurations.
Okay, thank you.
To validate all the configurations.
Any other question for Sini? Okay, thank you. Thank you, Sini,
Thank
for a
you.
very lucid presentation on a very complex topic. May I request Rovana to hand over the certificates? You have your team, you can call them. Thank you. Thank you very much.